Potential in fields, then. We're going to talk about gravitational potential, and we're going to talk about electrical potential. So let's talk about gravitational first. So potential. We've talked about potential energy before, and the connection between energy and work. Now, up until now, if you think about it, you've always talked about the change in gravitational potential energy because it's always been relative to something. There's your table, you've lifted something to a height above the table, and so now it has more gravitational potential energy than it had before. You've taken this as your relative zero, but of course if you'd taken the floor, you would have got a different answer. So really what we want is to have ourselves a zero of potential. So we want a zero of potential. Now if you think about it, potential energy is about, in this case, gravitational potential energy is about work done against a gravitational field. So if you're going to have a zero of potential, you're going to have a point where there is no gravitational field. So choose that then to be at a point far, far away, in the words of Shrek, far, far away from any other body. So let's choose infinity. This is a point as far away from anywhere and everywhere as it can possibly be. So we are going to say that our gravitational potential is zero at infinity. Now we have to decide whether in bringing something to infinity or from infinity, and whether we're doing work with or against the field, is positive. So if we say our potential is zero at infinity, and we say that we're going to do work against the field, so it is us doing work that is positive, then we get our definition of potential in a gravitational field. So the gravitational potential at a point is the work done against the field in bringing 1 kilogram from infinity to that point. So we chose to consider work done against the field as positive, and we chose infinity as our zero, and we chose to go from infinity to the point. Now, just before I forget, the units are joules per kilogram. So let's now get our formula. So the potential is Gm over R. But if you think about it, in a gravitational field, if I am going to bring my object from infinity in towards my planet, my 1 kilogram, it's going to be the field doing the work, right? Because gravitational fields are always attractive. So I'm not applying a force to bring this in. The field is doing that, and so the potential must be negative. It's not work done against the field, which would make it positive. It's work done by the field, which makes it negative. So you have a graph, all right? Do this properly. In the fourth quadrant. And if you think about it, if you were to take the gradient of the tangent to a point on that curve, there's my tangent. I'd be dividing a v by an r, so I'd be dividing this by an r and I'd get r squared down there, right? So the gradient of the tangent to the curve equals the field strength, G. So you have your formula for V. You have your graph of V against R. It's a 1 over R graph. Now if you compare that to what you'd have had for your force or field strength graph, you've got, let's call this G in newtons per kilogram and R in meters. You can see this graph is much steeper. This is a 1 over r squared graph. And you can see that if you work out the area under the graph, that is the value of G times the value of R, that's going to get you the change in potential, because it is the work done in going from here to here, or from here to here. So that's a very important relationship too. So the point I'm making here is that this graph, being a 1 over r squared graph, is steeper than the 1 over r graph that we drew for the potential. Now, it's also important to note for both graphs that we are asymptotic to the two axes. That this graph will approach but never touch the g-axis, and the graph will approach but never touch the r-axis. As r goes to infinity, g tends to 0, but it never gets there because there's never a point when g is 0. Likewise, when r tends to 0, you've got some constant over r squared. As that tends to 0, the value of g tends to infinity, but it never actually gets to 0. So it never actually touches the axis. It tends to infinity. So just an aside there, drawing the distinction between the G graph and the V graph.